See it okay? Thumbs up? Good. This was a topic I've been doing a lot of work on on some floodplains in southeast Iowa on the Cedar River floodplain. Eventually, you know, that Clear Creek might actually flow into there after it gets into the Iowa River. I partnered with just recently with Calvin Walter of the Iowa DNR, who was doing an assessment of land cover, how much row crop is in our 2-year floodplains across Iowa. And I said, hey, I've got a study that I've done down in the lower Cedar that kind of piggybacks on that. So I put this presentation together. Marion saw it and thought you guys might be interested. So for Marion's sake, it's a little slightly different than before, but very similar. So, okay. So this has to do with floodplain farming, you know, which is, I think it's kind of just lumped in with other types of farming in different landscape settings. And I think it has some particular challenges and unique opportunities for restoration if we think and isolate that setting by itself. So why farm on risky floodplains? You know, floodplains are going to flood. So what is it about these floodplains that farmers want to, you know, cultivate? Well, it's flat and it's relatively easy to farm, and it contains very high organic matter soils. So the water tables are shallow, we get abundant soil moisture, and, you know, combined, these landscape areas probably produce the best yields a farmer can have, especially during drought conditions. So you see quite an inverse of production relative to landscape setting. Like, these are the areas that produce very well during drought. In addition, you know, we know that it floods, and oftentimes, you know, as a 2-year floodplain, every other year, there's also an out for farmers. You know, why not flood when the USDA farm programs provide insurance against the negative consequences? So there's really no risk in many ways. So you get great yields oftentimes, and then when you don't get yields and it gets flooded out, you get indemnification for it. So it's kind of almost a no-brainer not to flood these or farm these areas. In terms of the alluvial soils, it's an interesting contrast between upland areas. So upland areas, of course, are constantly eroding, and we're losing organic matter and soils in the upland areas. Well, floodplains actually accumulate materials. They oftentimes accumulate thick A horizons because they are receiving the floodwater deposits loaded full of organic matter and debris and so forth. So they're constantly being replenished with nutrients. They tend to have a lot of sand, and they're very wet in places. So it's an interesting contrast in terms of soil processes, where one, we constantly build up materials in floodplains, and then uplands we're constantly eroding flood soils. So it's an interesting contrast. Before we get into the idea of floodplain farming, I think we should maybe take a step back and look at what's a natural floodplain look like? Now, there's not very many of those around. We've been doing work over the last, 10 or 20 years now at the Nature Conservancy. Owns some property on the Cedar River floodplain just by Conesville in southeast Iowa, where they have some property called the Land of the Swamp White Oak. So it's a very natural floodplain, has never been farmed. It's been grazed. It is being grazed right now, which is a different story, but it has never been farmed. So it's been an interesting place to look at natural floodplain features. The site there in the lower right is here on the floodplain. You can kind of see the width of the floodplain based on the forested areas and so forth. And there's a stream gauge right by the site, which makes it very handy to look at stream flows in the Cedar River relative to the groundwater levels. The site that we're going to talk about in terms of floodplain farming is actually about a mile south of here. So just a little bit off this map right in here. So we said that floodplains have high water tables and so forth. Well, they're also very closely linked to surface water stage fluctuations. So here's a water table in the middle of the Swamp White Oak property, about a mile away from the Cedar River, and you kind of see the stage in the Cedar River relative to the hydraulic head or the water table surface in a well in that property. You see that they're very closely matched. So the stage goes up in the river, water tables follow in the floodplain aquifer. If you zero in, say on one event, here's a picture of how that might look. You know, the stage goes up in the river. There's a lag time associated with it, and then the stage or the water table responds and increases in response to that stage. And this is a flood. This was not overland flooding. This really was in response to the stage in the Cedar River increasing. The little squiggles you see here on the center well and the water table are diurnal water table fluctuations at the water table surface from the large oak trees. That's a subject for a whole nother presentation. Interestingly enough, we've also done some work there to show that groundwater, even dissolved oxygen levels, are very closely linked to river stage. Here's how dissolved oxygen with a DO sensor installed in shallow groundwater at the site behaved. This was an optical sensor, so it was a more robust way of measuring DO. You see how it fluctuates, pretty highly oxygenated for water tables, somewhere between 2 and 8 milligrams per liter. And if you look at how that related relative to stream stage, it looks like there's some fluctuations, but it's kind of poorly timed relative to the stage, which is in purple there. But if you offset that by about an 8-day lag, the correlation increases quite significantly. So we see that even the DO levels in the shallow groundwater about a mile away from the river are influenced by how stage is affecting hydraulic heads, and in turn affecting groundwater dissolved oxygen concentrations. One of the things we've done out at the Swamp White Oak, again, this natural setting, is to look and see how does floodplain architecture or topography affect groundwater patterns. So we installed a series of wells in both ridges and swales within a pretty small area at this Swamp White Oak site. And there's a cross section we'll just show across here. The pink areas are high elevation, the greens and blues are low. You can kind of see how the floodplain accumulates and causes these ridge and swale topography. Take a cross section across here, you can kind of see how the floodplain topography rises and falls in a series of ridges and swales. Well, we installed 5 different wells in both settings, in a ridge and a swale, and then we measured the differences in groundwater geochemistry associated with these two environments. And lo and behold, you know, floodplains are known to be very patchy in terms of their above ground patterns, in terms of vegetation and so forth. Groundwater is also very patchy in these natural systems. And so what we see is differences between high wells or higher elevations versus low wells and low the swales. And you see that there's really a differences in groundwater geochemistry, where we have in the swales, we have higher specific conductance, very low DO, right next to a ridge that has high DO. So we see this interesting kind of pattern showing up because of this kind of ridge and swale topography. ORP, nitrate, phosphorus, DOC shows up across the board. So there's big differences in groundwater geochemistry within these natural floodplains. And we kind of mapped this out and just showed where we might see potential patterns emerge in terms of denitrification and so forth. We see where we see anaerobic water with high organic matter soils, we might see greater favorable conditions for denitrification. So we just kind of conclude with this saying that groundwater quality kind of exhibits this really complex spatial heterogeneity. Okay, so this is the background. Okay, this is a natural floodplain. Now we're going to go about a mile south and look at what happens when we farm these systems. This is, again, we're on the shores of the floodplain of the Cedar River. We installed a series of wells in conjunction with the Nature Conservancy. They were supportive of this research. They actually contracted with a local farmer to crop this area. It had been cropped many times before, but it had kind of been turned into a grass a little bit, reed canary grass for the most part. Well, they went out and farmed it again for the purpose of this study. And we installed some monitoring wells in these different environments, from kind of floodplain woods to kind of a reed canary / early sedge meadow kind of restoration, and then a cropland setting. This is the layout of the wells that we installed, kind of in a crossing pattern. We have 5 wells per land cover with a deeper well in the central part of each spot. So we have again, a wood setting, a reed canary grass, continuous grass, and then an agricultural site. So it's a kind of an interesting 3-well comparison of water quantity and quality across this three sites. What's interesting here is this is the LiDAR map of this area. You can see the ridge and swale kind of topography in the floodplains. This is the part that's been historically farmed. See, we lost all the variations of the ridge and swale topography. And so we just homogenized this topography under this probably, century or more of farming. If you look at the more color-coded LiDAR, you're going to just see again kind of the ridge and swale topography. This is this flat area that has been largely farmed over the years. Before doing some of this site work, we oftentimes like to go out and do some geophysics, just to kind of get a sense for what the subsurface might be beyond our simple well points. We looked at ground conductivity with an EM31. You kind of see it in the cropland area, we saw slightly finer textures, indicating a little higher ground conductivity there. Definitely more of a continuous sand at depth to in the other 2 settings. So there was some patterns here, and if you overlay the LiDAR topography, you kind of see that there's been some possible avenues of surface water inundation through this area. We did some deeper borehole stuff with the geoprobe tooling, and we're able to see largely it's sand down to about 14 meters across the site. There was a clay layer that's kind of uniform across here, and some of the row crop, you kind of see that differences in shallow ground conductivity that might show up there in the row crop area. So we monitored for a 3-year period, 2011 to 2013. Again, we had the gauge about a mile north of here on the Cedar River. You kind of see that in 2011, we saw a minor degree of flooding. This is the flood stage at that gauge. So maybe minor flooding showing up in 2011. 2012 was just a large regional drought across Iowa, across the upper Midwest. So you kind of see that there's very low flows in the Cedar River. And that drought, just at least in this area, immediately ended in 2013, where we saw big rainfall events over May and June, and just saw large scale flooding in the Cedar River. Well, what we saw is that, of course, this is the time period of planting across this area. So we saw massive flooding essentially 1 out of 3 years. And a 2-year floodplain, over time, that's about, not too different than what we might see. Minor flooding 1 year, massive flooding on a 3rd year. If you look at our water table fluctuations, again, in the woods, the crop, and the grass, they're all just mimic each other. The woods are slightly lower because we had just a little bit higher land surface elevation there. But if you plot them all together, they're exactly the same. So the water tables behave very similarly among here. The water table depth, anything above 0 means that we had standing surface water at the site. So we had a little bit of flooding in 2011, not much early, a lot of flooding, upwards of 1 meter of standing water above the site in 2013. And so because of that, there was no crop planted in 2013. So like I said, the Nature Conservancy contracted with a local farmer to farm that crop area. It had been in grass beforehand, and so in April of that 2011, the grass was burned. There was some herbicide applied that we didn't really monitor, and the field was planted in soybean. In June of that year, field applications included MAP, monoammonium phosphate, 40 pounds per acre, and potassium KCl at a rate of 70 pounds per acre. Glyphosate was applied for weed suppression. Again, we didn't really monitor that. In the next year, it was planted in corn, and granular application of NPK was applied in preparation from corn, side dressed with liquid N, urea ammonium nitrate, at about 220 pounds per acre in June. So we had soybeans, we had corn with very typical, very traditional fertilizer applications. In 2013, the field was not planted due to wet conditions and flooding, and it was planted with a cover crop as preventative cover in rye and radishes in 2013. So we had soybeans, we had corn, and then we had no planting because of flooding. So what did we see in terms of nitrate concentrations? This is all the wells, all the shallow water table wells. First off, you see is that under the grass and under the woods, we really saw no nitrate concentrations in the grass, a little bit in the woods, but not very much. In contrast, the row crop areas, again, this is 2011, 2012, 2013, really exploded high, okay? These are all paired sites. They behave hydrologically exactly the same way. This is not a flood pulse coming in, or else we would have saw it in the grass in the woods. This is a direct result of their agricultural management. So we saw nitrate concentrations almost at 80 milligrams per liter in the shallow water table beneath the ag field, all of which showed very little nitrate concentrations in the soybean year, really explode after the 2012 liquid N applications, and even through the preventative planting and no crop year remain very, very high. If you look at other water quality conditions there, we saw, some variations in terms of other groundwater quality patterns. Just because we're a little bit higher levels of, or maybe a little more slightly finer textured, we saw differences in specific conductance, I think relate to more of the lithology. Some differences in DO, DOC, when they're different letters, they were slightly different. Huge differences, of course, in the nitrate. Some minor differences in dissolved phosphorus. Most of these differences relate more to the probably lithologic patterns, kind of similar to what we saw with the ridges and swales at the Swamp White Oak site. You saw differences in slightly anaerobic conditions in the cropland, so forth, with lower DO, and so forth. So there were some of these patterns that are still left over from the lithologic differences. So to put them all in the same graph here with the land cover management. So in 2011, these are just average grass and wood sites compared to the different wells under the crop. So again, we had 5 wells in the cropland, the ag land cover. No concentrations of soybeans. Again, mid-year in the corn, they started creeping up, and then with the fallow and the flooding, we saw massive increase in nitrate concentrations. In terms of specific conductance, we actually saw a decreasing specific conductance in the grass and the woods, and an increasing specific conductance in the crop. I think could be traced to maybe some of the KCl applications and so forth. And if we look at actually the deeper well in the ag site, you kind of see that potassium chloride was applied in 2011, still very low in chloride. And then by the time 2013 came along and we saw some flooding, maybe some enhanced recharge, we saw chloride starting to creep up in the deeper well. So it kind of made it made an appearance at deeper horizons now by 2013. So in summary of this study anyway, the water quality really does, there's a legacy of the water quality showing up, especially in association with the corn rotation and the fertilizer applications. Even before the flooding that occurred in 2013, we were starting to see concentrations in the corn in response to the fertilizer applications. But even during the non-planted fallow year, we saw high concentrations show up. So this sort of level of application and crop failure and so forth can really generate some high concentrations. And here we had crop failure 1 out of 3 years, which is kind of consistent with historical flooding. So just to take this a little bit more general across settings, I was curious how much row crop farming is actually happening on floodplains. If you look at the English River watershed, this is a watershed just south of Clear Creek in southeast Iowa. We've done a lot of work across the state now, mapping floodplain elevations and floodplain inundation levels. So now we have pretty much maps across the state showing what areas of the floodplains are under these 2, 5, 10 plus 100, 500 year occurrence intervals of flooding. So if we intersect the row crop coverage with these kind of flood inundation maps, we see what the land cover, how people are managing their floodplains in terms of this agricultural intensity. So how much of the floodplain is in these different intervals? Well, 28% of the land is in the 2-year floodplain. Okay, 28% of the land in the 2-year floodplain is in crop, which just seems really high to me. And it only represents 3% of the watershed. So it's like we've got this opportunity, as this is where we're going to end this presentation on, with seeing how much potential loss there could be of nitrate and probably other things under these floodplain farming. Well, should you convert this floodplain 28% of the land from crop to natural vegetation, it's really only 3% of the watershed area. So it's not really, it's a ton of cropland for the watershed. It's a big chunk of the 2-year floodplain. So lastly, I want to end with some other work we've done doing some SWOT modeling on the Raccoon River in west central Iowa. And this is just a portion of the Raccoon River. This is the South Raccoon River watershed that's in an older glacial landscape. It's not the Des Moines lobe, so it's older. We've got hills and we've got well-developed floodplains. Okay, so here's a very typical setting where you might see upland areas and floodplains in the same watershed. And we looked at comparing the nitrate reductions you might get from converting row crop land on highly erodible land, HEL land, versus alluvial soils. Okay, so we used SWOT to kind of do some testing on how much nitrate reduction could we get? Should we convert all the cropland on HEL ground versus all the cropland on alluvial soils? This is kind of a surrogate for the 2-year floodplain. And there's a lot of numbers here. I'm just going to highlight a couple things. So if you look at how much of that watershed land need to be converted, well, there's definitely more HEL ground in the South Raccoon watershed compared to the alluvial soils. So 36% of the ground in HEL ground, almost 12% of the alluvial soils. So there's definitely more ground in HEL. So if you convert all that ground, of course, you're going to see greater mass reduction. But what about the percentage of the reduction? So we look at, 22.7% of the ground converted from HEL to CRP, and we get a 28 or 29% reduction. On the other hand, if we convert 7.5% of the watershed and alluvial soils to CRP, we get almost a 16% reduction in nitrate. So for the same amount of, if you normalize it by area, we can convert alluvial soils from row crop to CRP and get nearly 1.7 times more nitrate load reduction compared to the HEL ground. So I think in sum, without really having a conclusion slide, what I think I've tried to show is that these cropland areas, floodplain farming is very vulnerable to nutrient loss. They flood often, they're very productive, but again, we've indemnified all the risk associated with it. Very vulnerable to loss. They've lost a lot of their ability to process nitrate because, again, they're adding new nitrate and also eliminated some of the variability and the patchiness that might promote some denitrification. And there's opportunities. It's not that much land in a watershed, and should we start converting some of that floodplain land from cropland to CRP, grassland, woods, we're going to see a proportional reduction in nitrate load for a watershed. So with that, I am finished, and I would be happy to take any questions you might have.
Thank you, Dr.